Lecture number 1 in Module 11 in the book Problem-Solving Guide for Electromagnetism and Optics, Mirrors and Lenses. In the previous module, we did the refraction of light at an interface between two materials with different indices of refraction. Here we have lenses and mirrors, light going through lenses and reflecting off of mirrors. Lenses reflect light twice, once when they enter from the air into the glass, and once when they leave the glass and go back into the air. So here's a diagram with a converging lens. There's the lens. Light comes in. In order to see what it does, we draw a normal, and then we calculate the angle. It's going into glass from air. It's going to bend closer to the normal. Now we have a second refraction. We put the normal there. It's going to get bent away because it's going into the air. So the net result, a converging lens, not surprisingly, converges the light. It's a very complicated situation. You got two normals, you got an index of refraction involved, and we're going to simplify that tremendously. The light can curve differently based on the angle, and the front angle can be different from the back angle, and of course the index of refraction can vary. We're going to simplify that. Just say, look, it's a thin lens. There's one refraction in the middle of the lens. So we draw all of our thin lenses. They look exactly the same, independent of the focal length. This ray gets bent down through the focal point if it comes in parallel, and that's that. So the lens shape is just representative of the type. So if you look at that, you say, oh, that's a converging lens. All of them look like that in the ray diagram. Diverging lenses look like that. We don't change the shape if the focal length's different. They all look the same. Converging lenses focus incoming parallel light to the focal point. So converging lens focuses the light, and that's the focal length. In parallel through the focal point, down through the focal point. Diverging lenses spread the light out. If it comes in parallel, it's going to spread it out as if it came from the focal point. So the focal point of a diverging lens is behind the lens. So if somebody's over here observing this light beam, they think it came from that point because they think light travels in straight lines. But when light goes through a piece of glass, it can refract. The focal length of a converging lens is positive because it converges the light. It focuses the light. We put a negative sign on the focal length of a diverging lens because it's behind the lens. It doesn't focus light. Lenses are transparent, so light goes through them. It's important to remember that because sometimes there's a mirror and light doesn't go through mirrors. It reflects off of mirrors. So here's a converging mirror. Converges the light. It's curved inwards. Incoming parallel rays get reflected, not refracted, reflected through the focal point. There's the focal point. The angle of incidence is equal to the angle of reflection. So when a ray strikes a curved mirror, we can get the angle of refraction by thinking about a tangent mirror, like this. A tangent mirror right there. It's tangent to the surface of the mirror. So this ray thinks it's a straight mirror and it just bounces off, so the angle of incidence is equal to the angle of reflection. We can put a radii in there. It's tangent to the curvature. And we can put in, there's the incident angle, and there's the refracted angle. If the radius of the curvature of the mirror is large, and the ray is hit close to the middle, the focal point is about half the radius. That's an assumption we make for thin mirrors, mirrors that do not have sharp a radius of curvature. So the focal length is about half the radius. This is the radius because it's perpendicular to the curve. Diverging mirror is curved the other way. Light comes in this way, and it spreads out the light. Incoming light is bounced outward, reflected outward as if it came from the focal point. So we trace it back behind the mirror, and there's the focal point. Somebody looking at this ray will think it came from here, but the light did not come from here. It's dark behind here. There's no light behind here. If you put up a screen, you wouldn't see anything. Diverging mirrors, like diverging lenses, have negative focal points. They don't focus the light. Converging mirrors, like converging lenses, have positive focal points because they do focus the light. So images that are seen through a diverging lens and by looking into a diverging mirror are never real. They're virtual. There's no image behind here. It's dark behind there, behind the mirror. If you placed a viewing screen here, an image would not be there. If you look at yourself in a flat mirror, there's no image there. You can see the image, but if you go behind the mirror and put a screen there, there's no light there. Much of this module involves locating the position of an image, the position of the object, its magnification, whether it's virtual or real, whether it's upright or inverted. So we have three things here. We have the focal length of the mirror or lens, we have the position of the object, and we have the position of the image. And then we have some details about the image. Is it upright? Is it inverted? Is it virtual? Is it real? What is its magnification? There's an equation that relates the focal length, the image distance, and the object distance. It's called the thin lens equation. 1 over f is 1 over p plus 1 over q. And it works equally well for mirrors. Same equation. F is the focal length, p is the object distance, distance from the object to the optical device, mirror or lens, q is the image distance, the distance from the image to the optical device. If it's a diverging lens or mirror, the focal length will be negative. You have to plug in negative into this equation, negative f, or else you get the wrong answer. If the image is virtual, its distance from the lens, q, will be negative in the equation. The object distance, p, is always positive. So this equation is one way to see what's going on, but you should always back it up with a good ray diagram that includes the relative positions of the object, the image, and the focal length. So let's try one. An object is placed 60 centimeters from a converging lens that has a focal length of 20 centimeters. Where's the image? Is it inverted or upright? Is it virtual or real? What's the magnification? So let's start with a good diagram. Here's our converging lens. There's the focal length, about 20 centimeters given. The object is 60 centimeters away from the lens. We need an object. Conventionally, an arrow is used, but we don't like to follow convention. So there's our object. To locate the image, we locate the position at the top of the object as seen by someone looking through the lens. There's the person looking through the lens. Light comes from the object through the lens into the person's eye. One ray that's useful, in parallel out to the focal point. There we go. In parallel out to the focal point. Right through the center of the lens. That one is straight because we assume the lens is thin. It's the thin lens equation. Right through the center lens is easy. It's a straight line. Get a ruler. Another ray that's often used is in through the focal point on the other side and then out parallel. So let's put the focal point on this side. So note that it doesn't matter which way the ray is going. So this one, if it comes in parallel, it's going to get bent down to the focal point. The ray goes the same direction, whether it's going to the right or to the left. So where they meet, that's where the top of the image is. There's the image. It's upside down. So we drew 3 rays, but in fact, every ray from the top of the object that goes through the lens will go through this point. That one, this one, all of them. The only reason we use those 3 rays is they're easy to use. Straight through the center lens, that's easy to draw. In parallel, out through the focal point, that's easy to draw. In through the focal point, out parallel, that's easy to draw. It's easy to draw a line parallel to the axis. This one, it's hard to figure out how to get that one. You have to be careful if you're going to get that one. So these are the three rays. You only need two of them to find the point. So note how we were careful to adhere to the scale. The focal point was given as 20 centimeters. The object distance is 60 centimeters. So this object is 3 times as far away from the mirror as the focal length. If we're careful with drawing the relative positions, we can estimate what the image distance is. If the focal length is 20, that's 30, 35, something like that. The focal length is about 1/3 the object distance. Now we can try to use the equation to see if it's consistent with our lens, with our diagram. So there's the equation. The focal length is 20 centimeters. It's positive. It's a converging lens. The object distance is 60 centimeters. We can plug it in. We can subtract 1/60th from each side. We can get a common denominator. 1/20th is the same as 3/60ths. And when we do that, we get 2/60ths, and that's 1/q. So q is 30 centimeters, and we're happy with that. It's positive, which means it's a real image, which means the light is converging there. If you stuck a screen there, you would see it because there's light there. Light is getting there. The object is inverted, and it's real. How do we get its magnification? It looks like it's smaller. How do we get it? And the best way to get it is to use the line that goes right through the center of the lens. This line is straight. It constitutes the hypotenuse of two similar triangles. This one right here, and this one right here. These angles are the same. It's a 90-degree angle, so all three angles are the same. Those triangles are similar. The vertical sides are the size of the object and the size of the image. The horizontals, that's the image distance and that's the object distance, and the ratio of those are the same. The height of the image and the object is you can get the magnification from that. So the magnification is the ratio of the height of the image to the height of the object. And we put absolute value sign around it because we don't want to have a negative magnification. It's just the size of the image divided by the size of the object. So for our problem, Q is 30. It's negative 30, but we take it's positive 30. So we take the absolute value of that, we get 1/2, and we're happy with that. It looks like it's about 1/2. This is consistent with the diagram, but that's always good when your diagram is consistent with the thin lens equation. Now let's do a diverging lens. So here's a problem. A diverging lens produces an image that is 2/3 the size of the object when the object is 30 centimeters from the lens. What is the focal length of the lens? Let's use the World Cup trophy as an object. There it is. It's 30 centimeters away. It's given. It seems like we don't have enough information here because we don't have Q and we don't have F. Let's think. The diverging lens spreads the light out. So the image must be the same side as the lens, and the object must be 20 centimeters away from the lens because it is 2/3 the size of the image. Remember those similar triangles. If the magnification is 2/3, the image has to be 2/3 of the object distance away. The object is 30 centimeters, the image has to be 20 centimeters away. Let's add it to the diagram. There it is. There's the image. It's 2/3 as big, it's 20 centimeters away. A ray that goes in parallel will diverge as if it came from the focal point, and it will appear to come from the top of the image. So let's put it in. We don't know what the focal point is, but we know that that ray is appearing to come from the top of the image, so we can put it in. Focal point's back here somewhere. We don't know what it is yet. We can calculate it. Another ray straight through the center of the lens. It's a thin lens that doesn't diverge. Let's put that one in. And remember that the observer is over here, looking through the lens. There's the eye. The observer sees the image 2/3 the size of the object, but light only appears to be coming from there. It's not really coming from here. If you put a piece of paper back here, a white piece of paper, to see the image, it would not be there. It's virtual. There's a third way that we can array that we can use. We already know where it is, but just make surezies. We can have the ray go in the other direction, in parallel, out as if it came from the focal point on the other side. And if we trace this back, humans think it goes in a straight line. We trace it back, it goes right through the top of the image, as it must. Any ray that goes through this lens from the top of this object must go through the top of the image. So the image is indeed 20 centimeters behind the mirror. What do you think the focal length is? That's 20, that's 30. This looks like 60 about. Let's see what the equation gives. So there's the equation. 1/f is 1/p plus 1/q. The object distance is 30 centimeters. We determined that the image was 20 centimeters away from the mirror. It's negative. That's a virtual image. If you put 20 centimeters into that equation, you're going to get the wrong answer. The image is indeed 20 centimeters away from the lens, but it's virtual, so you have to plug in minus 20. So 1/f is 1/30 plus 1/minus 20. Get a common denominator. 1/30th is the same as 2/60ths. 1/20th is the same as 3/60ths, and it's negative, and that's 1/60th, and it's negative. And we better get a negative number for the focal length because it's a diverging lens. F equals minus 60, and we're very happy with that because that was our guess. Yahtzee. That's lecture 1.